Hello, General Biology, and welcome. This is section 1-2 of chapter 1, and we're going to talk about exploration and discovery, and we're going to look at where the ideas come from that we use our scientific methodology on. And you're going to find that the scientific methodology is going to be very closely linked to exploration and discovery. So, as we said before, when we think about the steps of the scientific method, which you're all familiar with, one of the things that you probably think of automatically is that, well, it starts with a problem. And as I said, you're right, we do. We start with a problem, but before we can identify a problem, we first have to make observations. Oops. Don't know why my pen is not working on this one. Let me pause this for a minute. Okay, so scientific methodology is going to start with the observations that we mentioned. And then once we get those observations, we can start to ask the questions, the whys. And that's where our scientific attitude comes from. And we all really do have a scientific attitude. You know, think about the summer. Maybe you were on the beach and you saw, usually around July, there's some jellyfish that start to float up and come in with the waves. And you've probably looked at it and thought, you know, why? Why does that happen? And maybe you know why, maybe you don't. Possibly you're walking along the beach and you notice there's these little holes that pop up by the water, tiny little holes. And you might think, well, you know, where did they come from? Why are they there? The first thing you do is you observe, and then you're asking questions. So you automatically have that scientific attitude. Okay, so scientific methodology, as we can see here, it is the center of everything. And then from that scientific methodology, we can explore and discover. And that exploration and discovery, we can use the scientific method in order to be able to do that. We can gather data from scientific methodology, and with that data, we can communicate our results, or our results might lead us back to, oh, I have more questions. Let's do more testing. And then what can happen is with that scientific methodology, we can put what we learn, the science, and we can contribute to society, or society might give science more reasons that they need to study. So as you can see, it kind of goes around and around. Science and society kind of generate or move the exploration and the discovery. Communicating our results also helps to get people to explore and discover, and communicating the results we get from that is going to be able to help society. Okay, so good scientists have scientific attitudes and they share their scientific information. And again, when they share that information, it causes more explanation and more discovery. There's a natural curiosity that exists with most people. Have you ever babysat a little kid and they're at that stage where they're asking why? Well, that's curiosity. And I'm sure that you've asked why several times. You see something and you ask why. And skepticism. Let's take a look at this word skepticism. It's okay to be a skeptic. We're going to be talking about global climate change. And the climate is changing. All right, there's no ifs, ands, or buts. If we look at the data, it's changing. But there's a healthy skepticism as to what is causing the change. And that's okay if you're skeptic, if you don't agree because you have a different idea about it. But one of the things you need to do is be open-minded. Now, don't close your mind and say, nope, I'm not changing my views. Let the data, let the information help either strengthen that viewpoint or cause you to change that viewpoint. Now, I'm not going to be out to try to change what you think. but I'm going to offer the data that's out there and either help back up how you feel or maybe make you see things a little bit differently. And one of the things that you always have to be in science is creative. Creativity is one of the best tools scientists have to generate new ideas. Okay, so stay curious. When you see something, ask, what's that plant? Why is it growing here? Does it need water? Does it need sunlight? Okay. Also, use your prior knowledge. What information you knew before, try to use that to help spark more curiosity and lead to bigger questions, especially when we're in the laboratory. I love to see that creativity and curiosity happening. Good scientists are skeptics, as I said. That means that they're questioning and they're asking, they're trying to test hypotheses to see if they are valid hypotheses. They refuse to accept any explanations without evidence. So it's okay to be skeptical, but make sure that you have the evidence to back that skepticism. Scientists who disagree with hypotheses may design new experiments to test them. They come up with other ideas. And supporters of hypotheses undertake rigorous testing of their ideas because they want their results to be valid and they want to come up with the same results every time. If somebody were to repeat the same experiment, they want them to come up with the same results that they did. And as I said, it's very important to be open-minded. Make sure that you're willing to accept different ideas. You don't have to, that may not necessarily agree with your original hypothesis. And I'd like you to keep that in the classroom because we're going to be having discussions. And these discussions, you may not have the same point of view that somebody else has, but that doesn't make them wrong. Be open-minded and listen to what they have to say and respect what they have to say as well. And I would like you to use your creativity this year because researchers, scientists are very creative. They come up with ways of designing experiments that yield accurate data. As I said, you're going to design an experiment. I'm going to ask you to design an experiment, the very first one, maybe the very first one. And I want you to be creative about what you're going to do. I'm going to give you some things, and I'm going to ask you to develop an experiment on it. And we'll be doing that in class as one of the activities. And we have to keep in mind, we have to have practical problems. When I said the grass is green because elves paint it, that's really not practical. So we have to have ideas for scientific investigations that arise from practical problems. People living on a strip of land along the coast may face flooding and other problems. So that's practical. How can we solve that? And the questions inspire new hypotheses and new experiments. So, there's flooding that live along the coast. One of the things that we learned is we filled in the marshlands, and the marshlands used to take that extra water, that excess water, and that's what prevented the flooding from happening. So we can ask practical questions. If we know now that that's the situation, what can we do to try to solve that problem that exists? So we can form hypotheses and then experiment from there. Again, we have to consider technology. Science and society are very closely linked, and technology we're gonna call this technology a limiting factor. And a limiting factor is something that prevents the productivity. So this limiting factor of technology is going to prevent us from exploring and discovering if we don't have the technology to be able to go there and explore and discover. So technology and science and society, they are very closely linked with all of what we've been covering. If we don't have the technology to get inside a volcano, then we're going to have to just make hypotheses and inferences based on the data that we're able to obtain. But if we can create technology to get into the volcano, then we can actually see what's going on. So that's what we mean by a limiting factor. Technological advances are happening very rapidly, and they impact life daily. Genetics is one of those fields that we're seeing rapidly increase because of our technology. Some of the new technology related to genetics is called biotechnology, and now we can mass produce complex substances like vitamins and antibiotics and hormones that were before only naturally available because of the technology that we've developed. So we need to communicate our results, and one of the things that we would do is, and these are some key concepts, we might look at what a peer review is, and we will talk about publishing peer review articles in scientific journals as ways of communicating our results. So a peer review is where scientists share their findings with the scientific community. They publish an article, and that article then undergoes a peer review. And that peer review is other scientists, they actually review the papers anonymously. They try to recreate the results, and if they're able to recreate the results and they think that the work is valid, then they will provide their assessment and let them know where it is valid, or they might say, hey, you've got some weaknesses here, go back and work on it. The next thing, if it is valid, they're going to share that information and they're going to publish it, and they'll publish that in a scientific journal. And again, in this scientific journal, you're going to be able to see the experiment and try to perform the experiment, and again, kind of like a peer review, but now anybody can do it. We're going to see if they can come up with the same results. So let's go back to our findings on that growth of the grass in the salt marsh. And we decided that it was limited available nitrogen suggests that that was a limiting nutrient for that marsh, and the plants were unable to grow because that nutrient was there. So now we can say, okay, let's see how this affects other similar habitats, and we can share that knowledge so that anybody else doing something similar can see how nitrogen can impact what they're doing. So we add to this scientific theories, a well-tested hypothesis that has been tested over the years becomes known as a theory, and these theories can tie other hypotheses together. One of the biggest things is that the word theory applies, and I want you to know this, the word theory applies to a well-tested explanation that unifies a broad range of observations and hypotheses that enables scientists to make accurate predictions about new situations. But one of the biggest things is that a theory must be able to be proven wrong in order for it to be valid. Okay, so that's what a valid theory is. It's something that must be able to be proven wrong. It's not considered absolute truth. It's held up pretty good, but it's not absolute truth. Okay, we're running out of time here. We're going to come back onto this page in just a few minutes. See you in a little bit.